This week and next week, we will see techniques that are very important in the context of energy systems, in particular, in general, and smart grid in particular. This has to do with handling uncertainty. In the OPF exercise we've done last week, we treated everything as known. We know what are the loads. We know, therefore, we can compute optimal set points for the generators. But in practice, it is never like this. In practice, there is always some uncertainty. Handling uncertainty is the topic of this and next week. We will see a number of techniques today and next week. So today we will see what is called robust optimization and a variant of it that culminates into affine feedback policies. And next week we will see model predictive control, which are two complementary sets of techniques. As I said last week, when we handle optimization problems, we don't care so much about solving the problem because, well, we care about solving it, but the technique for solving it, we take software that does it for us. However, what the software will not do for us is the kind of manipulation we will discuss now that has to do with quantifiers. So what is quantifiers? Well, it is, assume for some reason, we will see an example in a few more minutes. You can easily imagine the kind of reason for this. Assume we have an optimization problem like this. So it is a minimization problem. We want to minimize some function of U1, U2. That's a toy example. As you know from the lab already, you don't have two variables in general, but more likely in small cases, 20, 30, and in realistic cases, thousands of variables. But that's a toy example to explain the story. So assume we have to minimize some objective function, like we do always. We have a number of constraints on the optimization variables that I don't give here explicitly. And in addition, I have a constraint of this type. This constraint says this symbol means for all D1 that satisfies this. So what is implicit here is that D1 is a number, single dimensional number. For all D1 that happens to be between 4 and 5, and such that this relation that combines the control, the variables of my optimization problem, and this D1, which is called a disturbance, satisfy this inequality here. So a number of things about the terminology. When we have things like this, D1 is called a disturbance. What is a disturbance in our setting? It's, for example, the variability of the load. We predict that the load will be 20, but in reality, it might be anything between 15 and 25. Then we can treat the load D as a disturbance. It's not a given value. It is something that is known between, between bounds here. The disturbance might be anything that is predicted and is not certain, or it may be other causes of uncertainty. So that represents the uncertainty. This quantifier here means that the constraint we put on the problem must be satisfied for every value of the disturbance. So here, that's the constraint. Perhaps it's a constraint on the power line, on the power flow on some line, or the satisfaction of some user. And here, it's a constraint on that defines what is the set of disturbances. So we have two distinct roles play here. Also, when we have a quantifier, whatever comes after the quantifier is called a dummy variable. Just like in integral, if I say integral of sinus x dx, x is not a variable that we care about. We can call it x or u or w, that doesn't change anything. It's called a dummy variable. Here it's the same. This d1 is a dummy variable, which means in particular that the optimization variable is u1, u2, not u1, u2, d1. Which concretely means the goal of the optimization problem is not to find a value of D1. D1 is not something that we will have as output of our problem. It is something that is in the constraints. Right? So it's important to realize this. This is not an optimization variable. It's a nuisance variable. It's a variable that we would prefer not to be present, but it is present. So we have to deal with it. And therefore, we're interested in finding an optimal U1, U2, not an optimal D1. Disturbance, typically, we cannot choose it. It's imposed on us by nature. We cannot choose what the future will be. We have to be ready for all the occurrences of the future. That is what is explained here. But we have to take a decision. Here, we choose U1, U2, not knowing D1, but being prepared for all the values of D1. That's the setting. Before moving on with this setting, we need to do a few exercises of simple manipulations of this. Here, those are the constraints we had in this dummy optimization problem. I'm proposing to remove D1 because D1 is a dummy variable. If I can remove it, that will make my job easier because I don't know really how my optimization software is able to handle this. In fact, it doesn't. It will not handle this for you. So we need to remove it. Here, I'm proposing two ways of removing. I'm saying this constraint, now be careful, the constraint is a constraint on U1 and U2 that contains a quantifier D1. It is equivalent to this, or it is equivalent to that. Which one do you think is a correct statement, if any? So that's a quiz that you can participate in and speak up with the number written here on the board. It's a little Monday morning quiz to get your brain back into speed after Balélec. I close the poll in a few seconds. Closing. It's a very elementary example, but if you understand this right, that's one of the steps that you will do in more complex settings that you will be able to do right. The correct answer is C. Both are true. Let's see why. I need a small elementary algebra by saying I separate the U and the D, and saying that this inequality is true is the same as saying U1 plus 2U2 is less than or equal to 10 plus 3D1. And then the first observation we do, which is at the heart of all robust optimization, one of the basic observations is saying that an expression is less than f of D1 for all value of D1 that satisfies some constraint here, is the same as saying that this expression is less than the minimum. If you're less than all the values in a set, that's exactly equivalent to saying you're less than the smallest value of the set. Right. So if I apply this here, after putting 3D1 on the other side, I see that this constraint is exactly equivalent to that. Right. That's the first step. Now, why is it interesting? Well, because this I can solve. That's an optimization problem on D1 only. It's very basic. It's in one dimension. We can do it without software. Finding the minimum of D plus 3D1 when D is between 4 and 5. Well, the minimum is for D1 is equal to 4, which gives 10 plus 3 times 4, 22. So we can compute this, and that gives 22 here. So that's the step we will use all over the rest of the course. When I have something like this, well, first, what did I do here? I transformed this constraint into another auxiliary optimization problem that I could solve. And now we find that the constraint is equivalent to this one here. Here I have removed D1, which is possible because we know that D1 is a dummy variable. It's not part of the optimization problem. I've transformed the constraint and removed actually D1 here. Let's see another example. Here is another optimization problem. It's almost the same as before, with the one difference. This quantifier, for all, is replaced by there exists. So just one character is different, but that radically changes the problem here. Because there is a quantifier, at least strictly speaking, formally speaking, D1 is also a dummy variable. We're interested only in U1 and U2. We're not interested in the value of D1, but we require that it exists. Now, if I do the same exercise as a minute ago, is this equivalent to any of those forms that I'm proposing here? Are you able to continue the reasoning? I close the poll in a few seconds. And the majority says C, which is correct. For the same reason as before, except now we have max instead of min. So saying that an expression is less than value of f of d for some value means that it's less than the max. Right. That's exactly equivalent here. So saying that u1 plus ud2 is less than d plus 10 plus 3d, or 3d1, for some d1 means that it's less than the max. Right? Because if it's less than d1 for some d1, then it's less than the max, and vice versa. If it's less than the max, then it's less than 1, which is the max here. And if I compute the max, I obtain 25. So similarly here, I was able to remove the quantifier and replace the inequality with quantifier by an inequality that is purely numerical and has no quantifier. So the optimization problem I had before is equivalent to this, which is now a standard optimization problem, one that doesn't have quantifier. Here's another variant of the same problem, of the same letters, U1, U2, U3, U1, U2, and D1. But now I consider D1 to be an optimization problem. So I minimize this function. Sometimes we don't, if we're a bit sloppy, or sometimes you read documentation or papers that say, here is my optimization problem, and they don't say what is the list of variables. That's embarrassing. They should not do that. Should always explicitly say what are the optimization variables. So here I'm explicitly saying it's U1, U2, D1. So it's almost the same as before, except now D1 is in the optimization variables. Right? Before I had a quantifier, there exists, or for all. Here I just put it in the optimization variables. Right? So same question. When I do this, is there equivalence with any of the two problems before? closing the poll in a few seconds. Closing. And the majority says B, which is the correct answer. So if I solve the problem with there exists, that means I'm able to find an optimal U1, U2 star for which there is some D1. Then if I consider this one as a variable of interest, then that will be a feasible set of variables for P3, and it will solve P3 at the optimal, and vice versa. So it's almost entirely obvious. Yeah, there's a formal proof later in the slides that we'll not discuss, but it's almost entirely obvious that saying there exists D1 is the same as this one. The only difference is that in this case, we don't care about D1. We are not interested in the value of D1, whereas here we care about the value, but just means whether you return the value or not, which is entirely different from this. For all D1 is not the same as there exists. We've seen that if we remove the quantifier from here and there, we obtain different set of constraints. But here, so the take-home message is, if there is there exists quantifier is equivalent to adding this in the supplement in the list of variables here. That's a trick that is practically always used whenever you have to manipulate optimization problems in the context of disturbances or uncertainties like we do in this lecture and next week. Sometimes, as some of you are working with other advanced techniques, then there's decomposition, for example. So you always have this trick that adding a variable is equivalent to saying there exists a D here. In fact, very often this is completely not even discussed here. So that's the first take-home message. If there is there exists, then no big deal. We can simply add a variable. And second, if there is a minimum or a max, if there are quantifiers with expressions, then we can get rid of them with this set of techniques here. The one we've seen is this one here. For all D less than is equivalent of the expression being less than the minimum, which I'll illustrate here. If I have some expression, which I call EXPR, some expression here is less than all the values of f of d. I'm plotting here on the x-axis f of d. Well, being less than all means that you're less than the minimum, which is shown in blue here. Saying that the expression is larger than all of them means it's larger than the maximum. And saying that the expression is less than f of d for some of them means it's in this interval between the red and the blue. So depending on the constraint we will have less than the max or larger than the mean here. So those are manipulations we will be doing a lot. So it's good to be familiar with them. That's, for example, the problem we've seen a minute ago are elementary, very simple in very few dimensions. Here is something that is a bit more realistic. In the lab, it will even be more complicated. So here is a OPF problem where I have variables, which are the loads. You recognize the OPF problem we saw last week. That's the DC approximation of a problem where I had to calculate the generator set point G to G3. And here I propose three formulations of the problem. One is here, where it says the loads are in this interval. So this is a compact form of giving two inequalities for each of those expressions here. Those are the power load, the power flows on the lines, power flow constraints on the lines. In the DC approximation, those are the generator constraint at the slack bus and at the two generators here. So here's one formulation of the problem. Here's another one that has quantifier, and is yet another one which has quantifier here. Is there equivalence between P and any of A and B? close the poll in a few seconds. Closing. I wait for a few more seconds for the results to improve. I do like some presidents in some countries, they wait for the election until they get elected. So here I'll do the same here. I wait until the good result is shown on my board here, which is not yet the case. So perhaps you can talk to your neighbor and verify your vote before voting. Voila, now the election has the good result, so I stop it. I close the poll. And the majority says A, which is the correct answer. Is the correct answer to a bad question. When the question was asking, what is the same as P? So if I write this, I've added L1, L2, L3 as supplementary optimization variables, which is the same as saying there exists L1, L2, L3 in an optimization problem with G2, G3. So A is the same as P. Why you were confused is perhaps, but it's not the interesting problem. The problem we're interested in is not A and is not P, is this one here. Here, what am I saying here? Here I want to find a set points for generators 2 and 3 that minimize the cost and is feasible for whatever value of the loads that are in these intervals. Here, this is what I have when I have a prediction interval instead of just a certain value here. So whatever the value of the load, so what we're interested in is in B. But the bad news is we cannot get B by simply adding L1, L2, L3 into the optimization variables. In fact, what are we doing when we add them here? We say we solve an optimization problem where we choose the L1, L2, L3. We choose the loads, which are the disturbances. But the disturbances, usually we don't choose them. They are playing against us, or they're playing independent of us. They are happening by nature, not by us. So we cannot choose them. So that's the framework where we will be working. So in general, we will have problems that are of this kind. They may be more complex than this. We will see in 1 hour a few more complex ones, but the simplest form is when we have disturbances is this one. We were interested in minimizing the cost of the variables of interest, the generator set points, for example. And then there are constraints that I can express if I have linearized everything as linear constraints that depend on a disturbance variable. And here, the constraints are separated. There is a linear term in U and a linear term in D, so everything is linear with respect to everything, both U and D. It's globally linear. That's the simplest of all cases here. So if I have a problem of this type, which is the problem B of the quiz a minute ago, what can we do? When we can do on this more complicated example, what we did 15 minutes ago on the very simple example. Saying that this is true for all D, here, this inequality, is the same as saying that. What did I do? I separated U and D. I put the control variables on one side of the inequality, the disturbance on the other side here. And then we have seen that we can remove the quantifier. If it's true for all, it's equivalent to saying it must be true for the minimum. So we can say that this constraint is equivalent to that quantity, the inner product of A and U, Aj and U. J is the label of the constraint, the jth constraint, is less than this. Now what is this? Well, that's the solution of an optimization variable with respect to the disturbance D, but does not involve the control U. So I can solve it offline. I can pre-process my problem, solve this. The result of this optimization problem gives you a number Hj, and then this is equivalent to this inequality here, which now does not have any quantifier, any disturbance, and solved the issue. So in general, this is our first recipe. If I have what I call a robust problem. So a robust problem is a problem that where in the constraints, I have the quantifier for all. I have a disturbance variable, and the constraint must be true for all value of the disturbances. We call it robust because this is typically interpreted as the disturbance being something unknown, and we must have this true for all unknown values, not just for the values that we predict, but for all unknown values that are within a prediction range, the constraint must be true here. Then we see that this can be solved by a pre-processing step. In fact, by as many pre-processing steps as they are robust constraints that involve the disturbance here. For each of those, I solve the right-hand side, gamma j minus this expression of d. I minimize over all the constraints on d. I obtain some value here, and then my problem is now a standard problem. So it's not very difficult. It means there will be probably a big problem to solve in the sense that solving this problem will mean solving capital J auxiliary problems. So, but solving capital J problem is not as bad as solving a problem where I've added the number of variables. So each of those problems are of the same size here. So let's apply this to in detail to our OPF problem of last week. Last week, we had seen the problem of setting the points, the operating points of the generators, G1, G2, G3, given a prediction of the loads that are given here. Now, if I treat those predictions as just central values plus some uncertainty, I might be interested in solving a problem where I want that those set points G1, G2, G3 work, whatever L1, L2, L3 within those ranges. It's probably much wiser because this will be approximately true, those forecasts here, but what happens if they are a bit different, which is very likely to occur, and if the system does not work, for example, if the slack bus is no longer operate to work within the range that it had the capability of, then our system will simply trip or will not work. So it's a good idea to have some uncertainty bound here. How does it affect the dispatch plan that we did last time here? So here we see the disturbance, what had been called D is now the true value of the load here, L1, L2, L3. And if I write my optimization problem, this is the problem I had before without the quantifier here. Now, let's look at the details of the problem. So as we know from last week, we need to choose only G2, G3, because from the DC approximation, where we ignore all reactive power and losses, there will be power balance between G2, G3 is equal to L1 plus L2 and L3 here. So here we assume that we have, in some sense, a game where we have to choose G2, G3, and nature, or disturbance, will choose L1, L2, L3 here. Now, the cost of that we'll have to pay now is not known a priori because G2, G3 is influenced by the disturbance and cannot be known in advance. It is the slack bus, G1, that will absorb the uncertain part of L1, L2, L3, at least in this formulation that we have here. We'll choose G2, G3. L1, L2, L3 will be whatever they decide to be, and it is G1 that will absorb the difference that will, in real time, adapt to the true value here. So that means we cannot simply take the formulation we had last time, because already the objective here needs to be discussed. And the objective is a random part. How can I optimize a random objective here? That's not possible. We need a well-defined function. So the question is, what should we minimize? The second thing that we have seen already is that the constraints must be adapted to reflect the uncertainty of the loads. And this, we've seen how to do it. We will simply say those constraints must be true, whatever value of L1, L2, L3. Let's discuss the first thing of the objective. How can we get rid of having a random objective here? So the traditional method is to consider the expected cost, which assumes that in some sense, we're able to put a distribution on the disturbance such that, or at least we have minimal information about the distribution, such that we can speak of expectation. We can compute average values here. So again, it's important to realize the terms of what we are doing. So we have to choose some control parameters, G2, G3. Someone else, nature, the random operation of users, will choose a disturbance D. And as a result of this, our grid, the grid electrical state, will be something random, which depends on our choice, U, and the choice of nature here. So that's the problem. That's this thing here we cannot entirely control here. The cost, which depends on our choice, if we choose to operate G2, then we pay for G2, but also there is a cost that may depend on the cost of the electrical state. If we add, for example, penalties for voltage like we did last week. So the cost in general depends on both. So therefore the cost depends on, because the state, I write it as a function of U and D, it's a function of U and D, which has this form here. So the classical form called stochastic optimization consists in computing the expectation with respect to D, when we treat D as something random, unknown, of this cost, and calling this the average cost here. And we get rid of this problem of having a non-well-specified optimization criterion by taking C bar of U, which is the expectation of this here. Then the problem becomes minimize the expected cost of the control, subject to, now the constraints are they should be true for whatever the disturbance. So for whatever value of the disturbance, there must exist a state X, which satisfies the grid equation and satisfies the constraints of the state here. In compact form, we have minimized expected value of the cost, subject to, for all value of the disturbance, the emerging state depends on X here. Here I've removed one quantifier at the expense of having to have an explicit form for what is the value of the state as a function of U and D here. That's a hidden complexity of what we're doing. The complexity, part of the complexity is the presence of quantifier. We've seen a minute ago how to get rid of quantifiers. But before getting there, before writing the problem, we will need to write it in this form. So we need to eliminate the variable X, which is the state. Let's do this for this problem here. This is my problem now with all the constraints due to uncertainty. I need to minimize the average cost. So G2, G3 are the values I choose. There's nothing unknown about them. But G1 bar is the expectation of the slack bus value given the values of L1, L2, L3, G2, G3. Now it's very simple because it's linear. If L1, L2, L3 are random, all I need to know about them is their average value, their expected value, which I call L1 bar, L2 bar, L3 bar. In this formulation, the bar values are not random. They are the point predictions that are well known. The true value will not be equal to that, but the predictions are well known. So I put them in black here. So that becomes my objective functions. Now, what are the constraints? Well, the set points that I choose must be within the bound here. And now, for all values of the disturbances that are within the prediction intervals I have, so I've predicted a value of 100 for L1, but if I want to be a bit safer, I know that with large probability, it will be between 90 and 110. So that's what I'm assuming. And then there must exist some electrical state. Now, the electrical state is theta, plus the value of the slack bus power, plus here I add also the line power flows, active power flows, that satisfies all those equations, which are the DC approximation equations here. Then the slack bus value must also be between the bounds. That is a constraint that involves both the red and the blue value here. And also those are the DC approximation values, and the power lines must satisfy the branch flows here. So all those formed here are the equations that say the electrical state is a function of U and D. So the electrical state being the theta and the p and all the, and G1 here. So to obtain a formulation on which I can work, I need to eliminate them, which means I need to do some work to solve for all the black variables that don't have a bar, so G1, P12, etc., theta 2, as a function of the red and the blue here. So that's what I'm doing here, because I want to put it in this form where the constraints of the state X has been eliminated here. It's painful, but not difficult. Everything is linear, so all I need is to solve those linear sets of equations that are, if it would be large, I would need to use MATLAB to solve them explicitly. But here, that's easy to do. Here, I obtain G1 is given by this, for example. Theta 2, I can solve these equations in theta 2 and theta 3. There's two variables. I can solve them, and this is what I obtain. The electrical angle of the second bus is equal to this formulation as a function of the load and the generator set points, and same for the power flows. That's the step I need to do to have this formulation. Once I have obtained this step here, I have a problem where I can replace all the constraints I had before by the values, where I replace all the black state variables by those functions in G and L here. So that's the problem I have at the end. So there is some work, as you can see, to transform a robust problem into a robust problem that can be solved with the techniques that we've seen of removing the quantifiers and adding auxiliary optimization problem. Here I've removed all the state, that to remove the quantifier, I will use the trick that we've seen before. I have a problem of this type, which has to be true for all value of D. So I have constraints. For example, if I pick one of the constraints, for example, this one, minus P2 max, etc. So this one here is one constraint, which must be true for all the blue values. So I will separate, put the blue on one side, the red on one side, and that will give me an optimization problem to solve. So if I look at one of the constraints, not the one I said, just another one, for example, the constraint on the slack bus power here, where the first constraint is that it should be non-negative. Then we see this constraint here that must be true for all L1, L2, L3, which is the same as that. So it means G2 plus G3 must be less than that. So here I have an optimization problem Q1 to solve with respect to L1, L2, L3 here. I solve it. Here it's not very difficult. I find the value of 6.6. So here is my constraint, G2 plus G3 less than 6.6. So if I do that at the end, for all the constraint I had, here is what I obtain. I have to solve with respect to G2, G3, and here are all the constraints on G2 and G3. I have removed all the quantifiers. I've removed all the uncertain loads. And here is the result here. Right. This is how my problem is obtained. Now let's assume I take the same, but I vary the uncertainty. Here I had plus or 10 megawatt of uncertainty on L1 and L2, and plus or minus 20 on L3. Now say I multiply by 5 the uncertainty, the bound here. I can do exactly the same technique. Of course, if I had programmed that well, the bounds were parameters, so it's just change of the parameters. And here is my transformation of the problem here. This is what the transformed problem will look like. What do you observe on this transformed problem? There's a problem here, right? It's an unfeasible problem. Right? In general, when we write optimization problem, we're already very happy to ask MATLAB to solve for it, but it may be that the problem is unfeasible. And when we will, if we have a problem that originates from the description of a system, probably with no uncertainty, no disturbance, probably infeasibility is very rare. It just means probably there's something wrong with my formulation of the problem. But as soon as there is uncertainty, that will happen very frequently. So we have to be able to check whether a problem is feasible or not. All linear problem or optimization problem solvers usually return the feasibility or not. Here it's trivial to see because the infeasibility is due to two contradictory inequalities. Sometimes it's more complicated. You have 300 variables and you have 600 inequalities, and then the solution of all these inequalities is not possible. That might be more difficult to see, and linear programming is able to do that. Finding the feasibility is one of the things that a linear program does, as well as finding the optimal solution. Here it's not possible. We cannot have a number that's larger than 5 and is less than 4.9, which means that there is no solution. It means that if the uncertainty increases, it's not possible. It's not possible to find in this formulation of the problem, it's not possible to find fixed values of G2 and G3 that will work such that the slack bus is able to balance whatever all values of the uncertain loads here. There's too much uncertainties. The constraint we find on the slack bus, for example, are impossible. That's a limitation of this very basic formulation. This basic formulation is basic in the sense that we know there is some uncertainty, but we still fix G2 and G3. And whatever happens with our uncertainty will be taken care of in real time by the slack bus. We tend to do that if we have a strong slack bus with respect to the uncertainty. So if there's small uncertainty and a very large slack bus, then that's good enough. We will see later today policy-based systems where instead of deciding G2, G3, we will decide for a controller for G2 and G3 that will adapt to the true value of the load such that it works. That's called policy-based solutions. We will see affine feedback control policy later today, and next week we will see model predictive control, which is another technique for solving this big problem. But in some simple cases, there's no need for that. So if G2, G3 are able to solve, if the uncertainty is small, it works. If it's too large, it doesn't work. Here I've solved the problem in MATLAB, and I'm plotting as a function of the uncertainty. So here I'm plotting the uncertainty on L3, but they are proportional in all others. So the point where we were last week, when the uncertainty is 0, and the point we discussed a minute ago is when the uncertainty is 20. And we saw that if the uncertainty becomes 100, it blows up. There is no solution here. And I'm showing here the expected cost here as a function of the uncertainty. Then we see that the expected cost increases, which seems obvious, but is a very important philosophical or economical thing to remember. If there is uncertainty on my system, in this 3-bus system here, for example, I'm obliged to choose things that are safe, that are on the safe side. They must work whatever the loads. So by being on the safe side, I cannot be optimal. If I know after the fact that the true values were exactly something, so if the uncertainty were 0, I can find a value. If I know the uncertainty is 0, I can operate for some values of G2, G3 that will be the least expensive ones. But because there is some uncertainty, I have to operate over an entire range. Some of the values of the load will lead to more expensive values of the set points, and by robustness, I need to adapt. I need to be in that region. So if we allow even a little uncertainty, we see that we have a significant increase on the cost of the operation here, which we know from real life, right? If you have to manage uncertainty, they will come for a cost. That's why there is the business of insurance companies. Right? We're ready to pay premium to an insurance company to cover the unknown things. But very often there is a very scientifically wrong method that consists in saying, if I had known, I could have done this and it would have cost so much less here, which is true, but you had not known. So the fact that you don't know means there will be a cost and we have to pay for this cost here. In a smart grid, that's the cost of uncertainty due to renewables, as we will discuss next week when we talk about demand response and a number of things. Having some solar panel generation that costs very little, perhaps a few cents per kilowatt hour, is not the same thing as having it completely dispatchable, because this thing, it will be completely random. So the fact that it is random has a cost. So we cannot expect that the value of this is exactly the value of a kilowatt hour is not the same if this kilowatt hour can be dispatched, if I can have it whenever I need it, or if it's given by nature and I have it only when it decides to come. Because in order to manage this disturbance, the fact that the PVs or the wind generation has some variability, we will need things that will cost money. That's an example here. If you assume that L1, L2, this variability of L1, L2, L3 is due to the presence of embedded power solar panels here, we see that there is a hidden cost. So that will be the topic of grid regulation that we'll discuss a bit next week. Here's a small variant of this example I've seen before, which is called chance constraints. In this very simple example, I have said in order to make sense of my optimization criterion, I needed to be able to make sense of what I call the expected cost. And for that, I needed to have some information about the distribution of the variance, of the disturbance. But because everything was linear, the only thing I needed is to have the average value, which in some sense meant I needed to know what is the point prediction, what's the expected value, and what is the uncertainty bound. That was true in this simple case. If I take a more complicated cases where the cost is quadratic, something that happens for some generation systems, where the cost is typically quadratic is perhaps too simple, but that's a better approximation than linear, because it means if I try to generate more, the cost of generating more is more than proportional. That's true for many fuel-based systems, where they have an optimal operating cost. If you try to generate more, then they start being less efficient, and the cost increases. The losses in the system increases, and the thermal to mechanical power conversion becomes less efficient. So let's assume this is the case. The cost of generator is not linear, but quadratic. Now, if I do this, and I will have a problem, because if I remember the cost of the generator 1 is equal to the cost of this function here, which is now a random variable, square. So I need to find the expectation of something square, which means I need to know not just the expected value, but also the variance. So I will need to have some information of the variance. So by basic stochastic probability 101, if I want to compute the expectation of something square, it's equal to the variance plus the mean to the square. That's one. In fact, there's a definition of the variance. The variance is equal to the expectation of the square minus the mean square. So something we forget sometimes, but that's, so here we're interested in the expectation of the square, which means the variance will play a role. So if I do the maths and manipulate everything to get the cost, we will see that the cost will depend on the expected values. G2, G3 are my set points that I will calculate. They're not random, and this plus the variance of the load 1, load 2, load 3 that will generate some cost here. So that's something we see also very often. One way to capture the cost of uncertainty is saying that there is a cost proportional to the variance here. So if I have this quadratic thing, I will need to be able to have some information about the variance, and this is the optimization criterion I will need to minimize here. We'll need to minimize this with respect to G2, G3 with a fixed term, which is here the variance. Now, the second problem we have in such a case is that if in order to obtain the variance, I have perhaps made some assumption about the loads here. I know from statistics of the load, or that are published, for example, by some forecasting companies, they will give us the mean value and the variance. This is what I needed here. That solved my problem of the cost, but that did not solve my problem of the constraint. Before, I had constraints saying the load is between two bounds, and that's perfectly what I needed to solve the problem. Here, if I'm saying the load has a normal distribution, well, that doesn't give me bound, at least not strictly speaking. A Gaussian distribution is takes all possible values from minus infinity to plus infinity, which certainly doesn't make sense here. The load will not be minus infinity, or cannot take very large negative values or even non-negative values in this simple example here. What is often done is to replace deterministic bounds by what is called chance constraints that are true with some probability. For example, here, if I take a probability equal to 1 minus this, 10 to the minus 4, so 0.99999, 4 nines. I want this to be true with 4 nines here. Then I want my 3 random variables to be with some bounds, so I can compute for each of them a threshold here. And since I repeat 3 times independently, the probability of violation is the product of the probability of violation here. I go to the table or to the MATLAB function for the tail distribution of Gaussian, and I will obtain here, for example, with eta equal 4.15 for this value here, I will take the mean value plus 4.15 square roots. So those are the standard formula for translating a coverage interval for a Gaussian variable, having a coverage interval, which is true, with some probability. So here we're cheating a bit. We're saying we're not able to really solve the problem in a nice way, so we transform the constraints into something deterministic, which is true with some probability, which means that there is a probability, that our problem formulation is wrong, in fact, that the thing is violated. How much this probability will be depends on the system, how we are using the system. Sometimes it's done empirically. Sometimes it's done more mathematically. For example, for most distribution grids, we accept a failure probability of, not a failure probability, but a downtime of 2 hours per year. So we accept that power gets out 2 hours per year. And in fact, in the past years, that's more or less what has happened, more or less exactly. So there is a power cut for once in a while. And the power cut might appear because of our failure to model the system. That's a bit stupid. That happens, but that may happen. It happens more often due to a failure, something, a true failure. For example, 2 weeks ago, there was a power cut on campus that you've probably seen. It was our friends in physics in the plasma center who did some stuff that caused a short circuit and then caused a voltage drop on the medium voltage of the campus that caused all electronic equipments to, the voltage was 33% of the value. We've seen last week when we do voltage control, we accept 5, perhaps 10% variability. If we go below, most power electronic equipment will stop working. So all the routers, all the beamers, everything, they stopped working. For the beamers, this was no big deal. The bulb did not die, but for routers, it means all the EPFL network was down or had to be restarted, which took more than, the failure itself lasted for 140 milliseconds, 7 cycles of that. So there was a automatic failure recovery, but during 7 cycles, 7 times 20 milliseconds, that's the time it took for everything to reconfigure itself. That was sufficient to bring everything down. So that happens. It's not the end of the world, and that's why we accept also some epsilon here. Now we have this. We have something that must be true for all, and we know how to get rid of this here. So in summary, when we do real stuff in an energy system, and in a smart grid in particular, we have to solve problems that are of this form. We have a control point we want to choose. We have a disturbance that are played independently of us. And one formulation, there's many different formulations, but the most widespread one is this one. We minimize the expected costs subject to feasibility, regardless of disturbance, with high probability here. And then that leads to a problem, which is one of the problems we saw at the beginning of this lecture. Minimize some deterministic function of the control, subject to constraints that must be true for all value of the disturbance within a set. And then we get rid, if the constraints are in this well-separated form, we know how to solve it by solving a number of auxiliary problems, one per dimension of this set of robust constraints. Voila, that's all for the first hour. So we do a little break. Having a cost which is expected. And the constraints made deterministic by what is called chance constraint. Sometimes we prefer to use a slight variant of that makes the problem a bit easier, which is called robust optimization. More difficult part is just to know what's behind the terminology. The framework is the same. We have a control to choose. Nature will play a disturbance. The system state is the result of both. And we pay a cost that depends on our choice of the control and the resulting state here. In robust optimization, we want to avoid having to speak about distribution. Instead, we just assume that bounds are taken. So we assume that the disturbance lives in some bound. A bit like I did at the beginning of the course today. I assume, well, we don't know exactly what's the load L1, but we know it will be between 90 and 110. So if we have this and we don't want to speak at all about distribution, then strictly speaking, we cannot speak of the expected value if we don't have a distribution here. So this is removed by, instead of looking at the expected cost, we simply take the worst case cost here. So we minimize the worst case cost with respect to the disturbance here. That's what is called robust optimization. Does it make sense? Is it a good thing to do? It depends. And most of this consists in translating a real-life problem into an optimization problem that can be solved by MATLAB. So there are multiple ways of modeling the same reality. That's one of them. A criticism that's made of this is that, well, the worst case cost is something that's very unlikely to happen, and computing the control that is optimal for the worst case cost is often very non-typical and might be very expensive. Perhaps the worst case cost occurs when a number of things are bad and we need to force the control to take this value for this one. So it might be a bit pessimistic. What proponents of this method say, well, but the benefit, as we will see, is that it is considerably simpler. In particular, we don't need a distribution, we don't need to compute chance constraints, and there is also a very simple way to replace the max, as we have seen last week, and we don't need to compute mean expected values like we did with variance and things like this, like we did a minute ago. If we do this for our worst case, for our dispatch plan, then that comes the worst case dispatch plan. We just have the same problem as before, except now we say the cost I take is the max of the costs of this, the cost of G1 essentially. G2 and G3 are fixed optimization variables. So this is what we obtain here. The rest is just as before. So here I have not removed I have kept all I have solved all the problems I had before. I have computed all the constraints as a function of G2, G3, L1, L2, L3. So the step I needed to do to eliminate the state variable from showing up explicitly in the constraints, I had to do it here. So that's the problem I have here. Now that looks a bit complicated, but in this specific case, this can easily be computed. Here I have a max to compute. The max is over L1, L2, L3, which are three independent variables. So independent here, independent is a concept that is defined in many settings. It's defined for random variables. Two random variables are independent if the joint distribution as a product form. That's one definition of random variables. Here we don't have random variables, just have optimization variables that constraint. Here independent means that the set of a feasible value of the joint vector of the three is a cross product of three sets here, which means that the constraint on L1, there is a constraint on L1, there's a constraint on L2, and there's a constraint on L3. There is no constraint that involves the three letters L1, L2, L3 together. That's what independent here means. That seldom happens. So in the labs, you will not have independent constraints. So don't take that as a general case. But here in this specific case, when that happens, the optimization problem can be solved immediately because I need to maximize a function of L1, L2, L3. C1 is positive number. So what's the max value of this? Well, the max is obtained when L1 is max, when L2 is max, and when L3 is max, because the constraints are independent. So if I have a value of L1 that is not the max, I can increase the cost by increasing L1. And I can always increase L1 because the constraints on L1 are on L1 only. Whatever the choice I did for L2, L3, I can always increase L1. So I will increase L1 until I reach the max, and same for L2, L3. In general, that's not the case. In general, when you have a problem with 600 variables, 1,000 constraints, if you increase one variable, then you might be forced to decrease other variables because there are constraints that involve many variables together. So to make a long story short, the max of this is easy to compute, and we obtain 7.4 here. That's the max of the sum, which is when it's the worst case of the loads. And then, of course, this problem is easy to solve. We need to minimize this. And that, if you compare to stochastic optimization, the only thing that is different is that in stochastic optimization, we had taken here, at least if C1 is a linear function, we have to take the expected value, which was 7, and here is 7.4. If the function C1 is linear, that will not change anything because we can remove the constant from the minimum objective. The set point that is optimal will be the same for both here. If it is not linear, there will be a difference. So in this case, that's very simple. In general, of course, we cannot expect to be in such a simple case. So in general, we'll have to maximize a cost that depends on U and the control and the disturbance over all values of this disturbance, such that the constraints are satisfied also for all value of the disturbance here. Can we get rid of this max in the objective function? Well, the answer is yes, and that's very easy with what we've seen last week. We've seen that we can get rid of a max function by adding one supplementary variable. I call it here epsilon. I replace the max by epsilon, and I add the constraint that epsilon must be larger than all of the things that are here. So that means that epsilon must be larger than the problem. So in general, what we've seen last week is that if we have a max of a discrete set of constraints, we can replace it by an epsilon and add the constraint that epsilon is larger than all the constraints. That's what we've seen last week here. Here we can do the same. The only difference is that the set of constraints is not discrete, is an infinite non-enumerable set that for every value of the disturbance there is one constraint, but the technique and the reasoning applies the same way. I add one supplementary variable that I call epsilon, and now I must be that epsilon is larger than phi of ud for every d. Phi epsilon must be larger than phi of ud for every d. In addition, there are constraints on d that were the constraints that were true already from the primary definition of the problem here. But that's something we have seen an hour ago. We now have a problem to solve with one supplementary variable and constraints here. If those constraints are separated in U and D, then we can apply the solution we've seen before. That will lead to a number of auxiliary optimization problems to solve. So that's mechanically very simple to do, at least when everything is linear. That's why it's often used, because we don't need to imagine distributions, compute things on random variables. So if we do that here, we add this supplementary variable epsilon, and we add the constraint that epsilon must be larger than the cost of this for every L, which gives this one here. And that's the only thing that we have seen here. So at the end of the day, we can remove the for all epsilon by taking all the inequalities where I have the control variables. Now, epsilon is not really a control variable, but is one of the optimization variables that my program will return. It's not an optimization variable of my physical system. It's not a variable that I had at the beginning. That's one that emerges as a result of the transformation that wants to remove the max. Sometimes you read papers that explain, I do it, and there's an epsilon. And why are we choosing an epsilon? We're not choosing an epsilon. We don't care. The reason for this can be explained only by first writing the problem with a max, then removing the max. But now, it's a red variable. We need to choose it here. So we can use the method that we've seen before. Sorry. Yes, here it is. But before getting rid of this epsilon, little question. Which of those two, so here is the original formulation I had, which of those two formulations is correct? Where is my speaker? It's not so easy to do all the calculations, so you need to guess a bit for this. I close the poll in a few seconds. Closing. Majority says A. It's true that A is correct, but B also. The correct answer is C. In fact, B is the formulation we had seen before when we explicitly compute the max somewhere in the which was easy because we had we computed the max here, which was 7.4, the objective function, and those are the robust constraints we had before. We have seen before the break here. So removing. Now, this is the formulation we have if we first replace this by epsilon, and then we need to replace the for all, which will give this constraint here with this epsilon. Both are equivalent. Of course, if I have a choice, I would prefer B because there's fewer variables. But in reality, most of the time, the only thing we can obtain easily is A, because that results from a mechanical transformation. First, I get rid of the max by adding an epsilon. Then I get rid of the for all everywhere by solving one optimization problem per inequality. So that is typically what we will get for such problems. Voila, so that was, I would say, the step one of robust optimization, or optimization in presence of disturbances. What did we do? We said there is a problem with computing the objective function. We can even take the expected cost or the worst case cost. That gives those little differences and techniques on how to handle them. And then the big problem will always be the constraints. We'll have many constraints. That must be true for all value. So we must get rid of the quantifier. That's the optimization technique. But there's a fundamental problem, which is not just a solution technique problem, but is a problem in the nature of things that we have seen a minute ago, when if the uncertainty becomes too large, it might not be possible, or even if it's possible, it might not be economical to choose a solution that works for all cases. So the next thing we will do is to discuss adaptive policies, adaptive solutions, policies. So instead of choosing the G1, G2, we will choose a control law for G1, G2, assuming we can, through some feedback, get some information about L1, L2, L3. If they are larger than expected, then we can increase G2, G3 instead of sticking to the original values here. That's the control part of it. The first thing we'll see in control is affine feedback control, so linear control law. Linear control laws are very, very often used. They are very easy to implement, and they rely on a little theory that involves linear program duality. So we will say a few words about duality and linear programs. This is a subtopic of Lagrangian optimizations, of duality in general for optimization. Very often it's treated as a separate thing, so you have textbooks on duality and linear programs that usually take a different notation than the standard notation used in, for example, constrained optimization, which makes the story embarrassing and difficult, and you can easily confuse things and get the things wrong. What we will do here is first do a small recap on duality and linear programs. As you will see, at least as users, understanding why it works would be a full-fledged course on duality, and it's one of the beautiful achievements of maths to this theory. But we'll not look at the beauty, but just how to use it in a very safe way. And it's very easy because, as you will see, it's completely mechanical. But before getting to the easy thing, let's have a glimpse of the beauty that's behind by seeing how the duality of linear programs can be derived from the standard theory we've seen. So the problem is to say, I have a linear program. Linear means the objective is linear and the inequalities are also linear. And I want to build the dual program, the dual optimization problem of this here. So let's do it mechanically. If you remember from my cheat sheet of last week, I suggest to use Boyd and Vandenberg's reference. I need to write this I need to make a number of decisions. I need to write this with inequality constraints that are negative inequality constraints. I need also to find an objective function that I need to minimize here. And I need also to define a domain of definition here. And here there's a choice. Here I choose to say the domain of definitions are non-negative numbers. I could have put that into the constraints. That's a choice I can do. The theory works, whatever you do. So I do it like this, and then this leads to those inequality constraints, and the objective is x plus 2y. That's f0 here. So that's my choice of putting that into the canonical framework. I have already to take an arbitrary decision about where I put this constraint and whether I put them in the domain of definition or in the inequalities, and that was my choice here. The theory says that there are inequality variables, therefore the Lagrange multipliers are restricted also by inequalities. So there are two Lagrange multipliers that must be positive or zero. The Lagrangian that I need to obtain the unconstrained problem is the objective function x plus 2y plus lambda 1, the first inequality, plus lambda 2, the second. That's my Lagrangian. The unconstrained problem says that for fixed values of L1, L2, I need to minimize the Lagrangian. So that's over xy in the domain of definition. So I need to minimize this when lambda 1 and lambda 2 are fixed. Now if I number crunch everything, I put all the x together, all the y together. I have to minimize a linear function of x and y plus a constant here. So minimize ax plus by plus c over my domain of definition. That's the unconstrained problem. Now, that's fairly basic. If I need to take the minimum of a linear function, now, if one of the coefficients is negative, then the minimum is minus infinity. So that's easy. So the problem is unbounded. If both are bounded, then the minimum is for x and y is 0, and the minimum is c. So that's a very simple problem to solve. So the unconstrained problem is either unbounded, when one of the coefficients is negative, or when both are positive, it is bounded, and the optimal value is c. So the next step in the duality theory is to build the dual function. And remember that we need also to know when the dual function is defined. The dual function is defined when the problem is bounded. And the problem is bounded when the two coefficients are positive or 0. Now, the two coefficients being positive or 0, that gives two constraints on lambda 1, lambda 2. 3 lambda 1 plus 6 lambda 1 less than 1. That's because of this coefficient a here. That must be positive or 0. So that gives a constraint on lambda 1, lambda 2, and similar, the constraint on lambda 1, lambda 2 for the second coefficient. And when this happens, the optimal is easy. That's the term c, which is 5 lambda 1 plus 8 lambda 2. So the dual function is defined on this set, and when it is defined, it is equal to that. So the dual problem, the dual of a mean of an optimization problem formulated as a mean gives a max problem. That's the essence of duality. And as we will see, that's what is used for lots of tricks in optimization. We are able to transform a minimum problem into a maximum problem. So the dual of the original problem is maximize this, which is the g function, subject to the constraint here, and lambda 1, lambda 2 need to be in D. Need to satisfy those constraints due to the fact that they come from inequality constraints. So that's one form of the dual problem. There are other forms. For example, if I had not chosen lambda 1, lambda 2, x, if I had chosen a different D for this, I would obtain a different formulation. But that's one form here, which is in the literature on linear programs, is the standard one. I've seen that the dual of this is that. Now, if I look at it now purely in a pattern matching mode, I'm not trying to do science like I did by applying a general theory and derive this. I just do it like a monkey or like ChatGPT. I try to observe what has been done and repeat it. What do I see here? I see that the 5, 8 here are the coefficients that I see there. So those coefficients appear here. The matrix of constraint here, 3, 6, 4, 7, is the transpose of this. 3, 6, 4, 7 is the same but flipped here. And the 1, 2 here, the coefficients of the objective function, they show up as the right-hand side here. So this is generally true. If I have a linear optimization problem, here I'm just copying what I found on Wikipedia, which is correct. Wikipedia is most of the time correct, but never 100% sure. It's not really reviewed like a journal paper, but here it is correct. And so we had a problem of this form here, minimize linear function of the optimization variable, of this form, with inequality constraints and positivity constraint. Then the dual is obtained by taking the right-hand side of the inequality constraint as optimization coefficients, taking the matrix of inequality transposed, and the right-hand side of the matrix of inequality is taken from the coefficient that I had here, and I keep the non-negativity constraint here. If you combine all the possible cases, whether you have non-negativity constraints or not, you obtain this, and depending on whether you have inequality or equality constraints, you obtain those forms here. It is dual in the sense that it works in both directions. So the dual of something on the right is the thing on the left, and vice versa. The dual of this is that here. Here it's written in max. That's the convention used by Wikipedia, whereas we use mean, but we know taking a max or a mean is the equivalent. You just take the opposite of the objective function here. So the take-home message is computing the dual of a linear program is easy if you can first cast it in one of those forms here. Of course, there are mixed forms. You could have a form where you have inequality and equality here, but you can transform it by saying that an equality is a mixture of inequalities. Right? It's two inequalities, one bx less than b and minus bx less than minus b. Right? So if I minus bx less than b and bx less than b is the same as bx equal to b here. So if you're able to make this transformation, then you're able to compute mechanically, without having to think hard, what is the dual of a problem. And of course, as we know, the dual is transforming mean into max here, which is something that will be very important. So what is the dual of this program that I have here? It's a slight variant from what I had before. Here is to test your ability to work like ChatGPT. Closing in a few seconds. Dirac on B, 100%, which is the correct solution. You just pattern match and you will see that it fits with the second line here. Exactly, so we obtain this thing here. So that's the good news. We can transform the dual, we can obtain the dual of a linear program completely mechanically. There's no mathematical problem to solve. And now we will use this to do the theory that's the heart of a fine feedback control, which is solving robust problems with bilinear constraints here. We have seen how to solve robust problems when the constraints on the control and the disturbance are separated. Here I had constraints that are linear in U and D, and they are separated in the sense there is a linear term in U plus a linear term in D here. But in general, even if my problem is linear in U and linear in D, it doesn't mean it's linear globally in the variable U, D. In general, what it means is that it's linear if I fix D, it's linear with respect to U. If I fix U, it's linear with respect to D. And if I look at the two globally, I'm more likely to find something like this, where there's a common term, which I can cast in this form, which becomes quadratic, bilinear. It's linear in D and linear in U, but globally, there might be something nonlinear, which in the simplest form is gives constraints of this kind here. So that's the type of problem we're interested in. They are called robust problems with bilinear constraints. It's linear with respect to D, it's linear with respect to U, but it has a quadratic global dependence on both. Now, if I try to apply the previous problem, of course, I can try, but I'll have a hard time separating, because the previous problem consisted in saying I put all the D on the right-hand side, and I take the minimum with respect to D, which gives an optimization problem that doesn't depend on U. But now, if I try to do this, the result of this depends on U. So I cannot just solve the problem in a pre-processing step, because U is my optimization variable. So that's the problem we have. We will see this using essentially duality. And the key thing is that duality will transform a problem where there is a max. A max occurs because of the quantifier for all. But duality will transform max into mean. Now, if you remember, when there is a quantifier there exists, or a quantifier for all, in the very first quiz we did at the first hour today, if we change for all into there exists, we change the max into a mean. So that's exactly the trick, the idea that's behind it. Using duality, we can transform max into mean or vice versa. So we can also transform there exists into for all or vice versa. So that's another technique. We will get rid of the for all quantifier into there exists using duality. And then that's another technique, more complicated, as we will see. It involves duality, but it works for the cases where the simple method seen an hour ago doesn't work. I will explain it on an example before giving the general recipe. So here's my simple example. It's not, this is my numerical example here. It's very simple. It's only, the number of dimensions is so simple that I can solve it manually without the theory, but we will see how the theory works. So here, I have to minimize this linear function of U and V, such that for all value of a disturbance that between 6 and 7, this quadratic inequality is satisfied. It's linear in U, linear in D, plus a term that's linear, bilinear. So the generic form means there are quadratic terms. Quadratic means cross term. There should not be D squared, but there are terms in D, U, and dV here. That's the problem. That's why we cannot separate it here. So if I apply this general framework here, my dimension of the control is 2. The number of robust inequalities is 1, capital J is 1, and it is this generic form where this matrix that multiplies U is the matrix of coefficient 8, 9. The matrix that multiplies D is the coefficients 10 alone, and the bilinear term here is the matrix 11, 12. It's a row vector, but we can also see it as a matrix. So if I multiply 11, 12 by D on the left and UV on the right, I obtain exactly this term here. And the right-hand side, the gamma is 13. And the constraints on D are D is between 6 and 7, which corresponds to this, saying D times the vector 1 minus 1 is less than 7 minus 6 here. That's the type of steps we need to do when we use the basic functions in MATLAB to solve linear programs. I'm just transforming my inequalities into something that MATLAB can, that LinProg can understand. That's what I've done here. Okay. So I've done nothing. I've just cast the general framework, applied it to my specific case here. The step 1 is to get rid of the quantifier by introducing a max here. So the constraint J here, one of the constraints here, I rewrite it here by putting all the U on one side, and it must be true for all D here. So now the difference with before is that the optimization problem that I obtain depends on U. So saying that this is true for all value of D, right? means that the max of this is less than that. Right. So the max of this now is the solution of an optimization problem that depends on you, on my control. I call it P of U, my problem, Pj for constraint J. So P of U is computing the max of this. So finding the max of this, subject to all the constraints I have on D, that's an optimization problem that has a certain optimal value, and we know that this is equivalent to that. That's exactly what we did an hour ago, except what we did 1 hour ago, the solution of this pre-processing step did not depend on you. Now it's just purely theoretical. I will not compute the function P star of U, but theoretically I can write it in this way here. So this robust constraint is equivalent to this. The problem is the function P star is an unknown function, but I've done one step. I've removed the disturbance. Now I'm looking at this optimization problem. I have to solve. I want to get rid of somehow the P star here. P star is the optimal value of this optimization problem here. Now I will look at the dual of this one. As I announced, we will use duality as a major trick here. What is the dual of this? Well, using the techniques we've seen 15 minutes ago, we exchange the values, we take the transpose of the matrix of coefficients, etc. The dual problem, it was a max, it becomes a mean problem. It was on a variable D. Now there is one vector of variables that corresponds to the dimensions of the constraint here. So I introduce a vector lambda. It's for constraint J, so there's a vector lambda J that has the same dimension as the vector C here. So lambda J is a vector of same dimension as the vector C here. And I need to minimize C transpose lambda J subject to those constraints. That's by direct application of the duality thing. We still need to check that duality works if the problem is feasible. So it must be true that the feasibility constraints on the disturbance are the set of disturbance is not empty, which in general will be the case. Otherwise, your problem is ill-posed. But you need to be careful if you have a programmable problem where you have parameters. If you apply this and your set of parameters is such that your set of constraints is non-empty, then this theory might not work and you might have contradictory results. But in general, it's not a big deal. So if that is true, strong duality holds and my recipe works. So the dual of this problem is this one here. Okay. So this is what I've done. I have, in step one, I have replaced my constraint by this P star, which was the max of those. That's the solution of my optimization problem. And in step two, I say, well, that's the same as the mean of that. P star of U, that's an optimization problem, parameterized with U, with optimization variable D in its primal form, with optimization variable lambda in its dual form. And now it becomes a mean. Now remember the constraint, what consists in saying that this thing is larger than that, which was the max, because of the for all D. Now we just do things, now we don't think of our physical problem, we just apply mathematical transformation, and we say this constraint is exactly equal to that. I've just said that P star, by strong duality, is the mean. So this constraint, which was larger than a max, is now larger than a min. And now, bingo, here comes the magic and the beautiful thing of this theory. Saying that this is larger than a mean is saying that it's larger than one of the values. That's the quantifier, is there exists. So duality has allowed us to transform for all into there exists. For all value of the disturbance is replaced by for one value of the Lagrange multipliers related to the disturbance. So for one value of lambda, this constraint must be satisfied. And the following step, so we have reached this point here. We have to minimize our thing where the robust constraint is replaced by there exists for every constraint, there exists one vector of multipliers, one vector per constraint, so there's many multipliers at the end that satisfies this. And now we have seen that adding the there exists is the same as adding the thing as optimization variables here. It's trivial, but it's an observation that is less trivial to do when we have a complex problem with thousands of variables. Here, there exists here is the same as adding them here. So our optimization problem can be cast into a problem without quantifiers, so one that can be solved by MATLAB without quantifiers, but where I need to add for every robust constraint one vector that has the same dimension as C, here, the set of constraints of the disturbance here. So of course I have considerably amplified the size of my problem. I've added many, many variables, but I've made it non-robust here. So if I put everything together, here is the recipe. If I have a robust optimization problem with bilinear constraints, I can solve it by adding one vector of dual variables of size C here for every constraint. So there are capital J such vectors that I add to the optimization variables. And then I still have the same optimization function, the same constraints on U, but the robust constraints here are transformed by other robust constraints, which are hard to, it's possible to make sense of them, but it's a lot of work to make sense of them. So we look at them as pure mathematical transformation. Now, the bad thing is we have lost completely the overview of what the original problem is, but they capture, in some sense, the shadow costs of all those robust constraints here are captured here in those constraints. If we do this to our original problem, the little toy problem I had here, this is my problem with optimization variable dimension 2, the disturbance of dimension 1. How many dual variables do we add to this problem when we make it when we remove the quantifier? I'll close the poll in a few seconds. Closing. And the majority says A, which is not true. This should be. So we have one constraint, so we add one vector of Lagrangian, of Lagrange multiplier, which has the same dimension as C. So C is the vector of constraints here, and this is two inequalities, so there are two constraints, so we add a vector of dimension 2. So we add one vector, but there are two variables. So perhaps you answered one because you thought of one vector, which would be correct. So if we apply this theory, this is what we obtain. So this problem, minimize U plus 2V subject to this inequality being true for all D, is equivalent to minimize U plus 2V subject to these inequalities that must exist multiplies lambda and mu that satisfies those constraints that are given here. So admittedly, this now is hard to immediately interpret as a function of that. But the good news is that's completely mechanical. Getting this form is straightforward. Question?
Yes. In this development, I assume that strong duality rules of
Yes.
mind, because there is always one D.
Yes.
Such that.
Yes.
What happens if we put this problem and it doesn't hold?
Will
it still give a solution?
No, the theory breaks apart. So strong duality says, you remember, if there is constraint if the problem is convex and there's constraint qualification, then strong duality holds, which means the dual has the same solution as the primal, and the optimal for one is optimal for the other, etc. And in the case of linear program, constraint qualification always works, except for you need one condition, which is that the set of constraint is feasible. Otherwise, we don't know what happens. So there might be strong duality does not hold. So no, but if you look at what does it mean here? Here, that's the constraint. This set of constraint must be feasible. Well, in this case, now what I'm saying, you might have a case where you have somehow a parameterized problem where you don't have 6 and 7 as the bound, but they are functions of all your parameters. And if you're not very careful, you don't verify whether those functions are such that the lower bound is truly less than the upper bound. And if that does not happen and you apply this automatically, the result is wrong. We don't know. It may be wrong or right. We don't know. The theory has no result. So if I had something else here, essentially, if this set is empty, that means the set of D's for which this condition has to be true is empty. So this condition is always true. Right? It's robust with respect to something. There is no disturbance. The set of disturbance is empty. So a constraint defined on an empty set is always true. So I guess what it means is you simply get rid of those, you delete those, but by implementing, if you don't delete it, you will have 7 minus 6. Those two numbers will be, you will have them, but it will be wrong. You will have simply a wrong statement here. So as I said, it's true only if strong duality holds, which holds only if the set of disturbance is not empty. That's the condition. Let me skip this one perhaps and move to the real reason why we want to do this. So we have seen techniques of linear programming based on duality to transform a robust problem with bilinear constraint into a problem that is non-robust, where we have replaced the robust constraints by constraints that are of standard form, but with Lagrange multipliers instead. And again, I insist that's very powerful. You can go a very, very long way with duality. That's one of the most powerful theories that exists in mathematics. And let's see on the application to making control laws that are linear. As we have discussed, if we set G2, G3 to fixed values, that may be good enough if the disturbance is not very large, the uncertainty of the disturbance is not very large, with respect to the thing that absorbs the disturbance, which is the slack bus power here. But if it might be large, it's better to let the system adapt in real time. And what we want to do is compute ahead of time a feedback policy. For example, we will discuss that more next week, but in an electrical grid, there are two levels of controls that adapt things in quasi-real time. Primary, that adapts it instantly, primary control, and secondary control. So in this electrical grid here of continental Europe, in where we are, whenever more power is used or less power is used, all generators adapt their generating power by reacting to what is called frequency. That's primary control. And if the frequency based control, primary control, is not sufficient, there's a secondary control done by the so-called system operators like Swiss Grid, that monitors the power balance. And if they see that there is some imbalance in one direction or another, they send explicit signals at the time scale of approximately a second to all generators that participate in what is called regulation services. Your PV panel doesn't do that. Your PV panel does not adapt to power imbalance. But if you own a dam on your river, you have a nice property in the Alps with a river, you put a turbine on the river, you might decide to sell a regulatory service to Swiss Grid by reacting to the signals they give. And by grid code, you are forced to implement what is called primary control to adapt slightly the speed of your turbine to the frequency of the current. So this is how the things work in a grid. So we could imagine that in this grid here, we have through this indirect or direct form, we have some feedback that tells us some noisy estimate of the load, L1, L2, L3, and is used to transform the generators here. The simplest of all form is linear. So if we want the thing to be linear, and in the simplest form here, we take the global load, because we're doing the DC approximation. So in general, we can have one coefficient per load here that would just work as well, but make the problem more complex. So here's perhaps the simplest of all adaptive systems we could imagine. So the simplest of all control laws. We would say, for example, G3 is too expensive and we don't touch it. But G2, we adapt it with what is called a governor. So a system that will adapt the speed of the generator to the power generated to some input signal, which in this case is the sum or an estimate of the sum of the loads here. And the output is a constant plus a coefficient times the input variable. That's very simple. Whether it's optimal to be linear, no. In general, it's not optimal to do a linear control law. And we will see next week something that produces nonlinear control laws. That's model predictive control. It's based on an entirely different type of techniques. And in the lab, you will have to play with, or you will have to implement both, and you will see which one works better. A model predictive control is more complex in terms of the size of the optimization problem it gives. And this one is simpler. So this one is very often used, I would say, in small-scale systems, in particular in thermal system, building automation, a small-scale grid. That's something very, very frequently used. Because it's the simpler with respect to optimization theory. Still, we need now to compute U2 and V2. What we had done a minute ago at the first hour is a special form of this where V2 is equal to 0. If I say my control, the value of G2 is to be computed as a result of my optimization problem and should not depend on the load, then that means I compute U2. So U2 was the value we computed an hour ago, but now we say we add also V2. And V2 also needs to be computed, and this is what we will do here. Now since this is stochastic optimization, we still need to have a cost, define a cost value. So like we discussed an hour ago, since everything is linear, I can simply take the expected values and don't worry too much about the distribution. So the forecasted value of generator 2 will be this here. And my expected cost will be what I obtain when I replace all the disturbances by their expected values here. So I have now a framework like before, except that my control variables are now a bit more complicated. There are the two parameters of the control of the generator 2, U2, V2. I could do the same for generator 3, but for simplicity of this example, I don't do it. So G3 will have a fixed set point here. The disturbance are the same as before. The state is the same as before. The forecasted value is U2 plus 7V2. Why 7V2? Well, because 7 is the expected value of the sum of the loads here. So that's expected value of the generator. So the expected cost is C1G1 plus C2G2 plus C3G3. Now this parenthesis simply means the product is C1 multiplied by this. So that is the expected cost that will be my thing to minimize. Now, what are the constraints? Well, the constraints is the same as before. They must be true for all the values of the loads in this uncertainty bound. And here I have eliminated the state X. I've done that in all the examples of application. They require this step. And here you see the constraint on the slack bus minimum power, the constraint on the slack bus maximum power, the constraint on the power line 1, 2 in one direction and in the other direction. So those are now, if I know G1, G2, L1, L2, L3, I can compute those power flows and generate a G1. This is what I've done here. So it's the same as before, except now this value here was G2. Now it is a function of U2, V2, and L1, L2, L3. So this step is the same as before, no big deal. But now let's observe what we have obtained when we've done this step. I have to minimize some function. The problem is not with the minimization, but because I've removed the disturbance from the optimization criterion, subject to constraints that must be true for all value of L1 and L2, L3, and that must be true for my values of the red variables that I've chosen. And we see here there is these bilinear terms. There is a cross product V2, L2, for example. So not surprisingly, because I'm presenting this now, this comes exactly as a case of bilinear constraints in a robust optimization problem. So the good news is that, well, then we should be able to solve it. The bad news, it's a bit clumsy. It requires some identification of the model that is here through the inequalities that are here. So let's look at step by step. The first constraint is given here. The first constraint is the slack bus power must be non-zero or positive, must be non-negative here. So that is this constraint. And this is the bilinear part here. So I need to add one optimization, one Lagrange multiplier. Thank you. There's also a number of other windows you may want to close. So they are their feedback. They saw that you close the window. So the theory says I can remove one such constraint by, I can remove the L1, L2, L3 by, for every inequality that I have, take the dual of the problem, the implicit optimization problem, and add one vector of dual of Lagrange multipliers, which has dimension C. C is the linear description of the set of constraints for the disturbance here. Here that should be in blue. Now how many are there? Well, there are 1, 2, 3, 4, 5, 6 constraints on L. Right? Just like if I write this in matrix form, I will have a matrix L1 less than 0.19, another less than minus 0.19 plus 1, etc. So just we did this exercise for the previous example. That will lead to 6 dimensions. So I need to add a vector of dimension 6 to the first inequality, dimension 6, because there are 6 constraints on D. And I need to do that as many times as there are robust inequalities here. So if I do it for the first, and I use this trick of duality, so I use the mapping that I've given for this problem, I will add this vector with those constraints, and that will be added to the problem here. Those vectors must be non-negative. Now there are vectors that come from the coefficients that we have here. And as we saw last time, that's easy to do, but it's more difficult to have a physical meaning. If we do this for the entire problem, how many times do we do it? How many vectors of dimension 6 do we need to add? Closing the poll. So we see a small majority for solution H, which is 10, which is the correct answer. So that's the thing. It's not easy to do, but you need enough time to do it. You need to count how many inequalities there are that affects that affects both V and L. Here there's 1, 2, 4, 6, 8, 10. Right. So there are 10. So here's the general trick. We see so the general mapping. So the solution is given here. We need to identify the matrix D because there will be in the constraints of D. What is the dimension of the matrix D for this problem here? I'm closing in a few seconds. Majority says D, which is 6, 3 by 10, which is not correct. Where is it? The correct answer is C. Right, so the vector D has 3 dimensions, so the matrix has 3 columns. Now, how many inequalities there are? Well, you have things like this. Those are 2 inequalities. So there are 6 lines here. Depending on which order you take the inequality, you'll have different values of the matrix D, but you will always have that number of inequalities. And at the end, how many optimization variables do we have in the transformed problem? Closing the poll in a few seconds. Closing. Majority says H, which is wrong again. H is true. There are 60 Lagrange multipliers that are added, but you still have the 3 original variables, U1, V1, and G3. So you have, in the original problem, you have all the U's, which were 3, plus all the Lagrange multipliers. Correct. So we had a problem with 3 variables of interest. If we make it non-robust, we pretend L1, L2, L3 are known. Then we have 2 variables of interest. We need to compute G2, G3. If we want to do a control law, then we have 3 instead of 2. But of course, by doing the control law, we need to have robust constraints, otherwise the control law doesn't make much sense. But the size of the transform problem is increased by the dimension of the uncertainty, the number of inequalities, which is 6, times the number of constraints we have. So that typically is a large number. It's not exponential, it doesn't grow exponentially with the size of the problem, but you should expect that robust optimization will lead to big problems. This is why it's done essentially with linear problems. We will have a tendency to linearize everything if we want to do it in a robust way, because we're able to solve linear problems of very, very large size, up to hundreds of thousands of variables. But from a programming viewpoint, as you will experience in the lab, there is some work into making this problem the correct problem. So I did it for this small problem here. I'm assuming I'm now increasing the uncertainty, like I said before. This is what we did before. If I have a fixed value of G2, G3, this is the cost I have, and it blows up at 100. When the uncertainty here is multiplied by 5, the factor is 5, then the problem is unsolvable. We see 2 things here. We see that the cost is less, not dramatically less here. That depends on the examples. In some other examples, the cost must be more, the gain must be larger. But more importantly, and that's invariably what happens when we do robust optimization, if we don't have an adaptive things, very quickly it becomes unfeasible. And here we've seen that it remains to be feasible. There's still a point at which even the control law becomes unfeasible, but here it's double. It supports an uncertainty that is double. So the feasible region is much larger than without feedback, and that's, on this simple example, is double. On examples that have large number of unknowns, of variables and constraints, the improvement gets much more dramatic. In fact, if you try to do robust things without policy, very often it simply doesn't work when you have too many variables here. Voila, so the lecture is a bit more technical today, but that's the reality of things in energy systems. Handling uncertainties leads to problems with control and disturbance. It's important to pose the problem well, recognize that a thing is a disturbance or a control, because they will be handled differently. In front of the disturbance, there will be a quantifier, and we will need to get rid of it. There is always an issue, and the cost somehow needs to be made independent of the disturbance. Expectation makes a lot of sense. Worst case makes sense sometimes, but it's also easier to work with, as we've seen. And the hard thing will always be that the constraints must be feasible for all values of the disturbances. In the good cases, we can pre-process the constraints by solving them one optimization problem per constraint. In the bad cases, we may need to do more work, like we've just seen. And in general, it's better to compute an optimal policy than an optimal static set point, but it will come at some cost. Voila, we finish a bit earlier today, but the quiz is a bit more technical this week. So, because as you can imagine, you will need to dive into equations and things like that. Voila, enjoy the quiz and the lab.